the topic of today's talk will be about 3D finite element method simulations. It will be related with our product, but also you could draw some conclusions, like a general conclusions from this talk, and decide yourself whether 3D FEM simulation is for you or not. Because as you will see later, so that not, let's say, not all the problems should be and could be solved with 3D FEM. So let's begin with our story. The outline will be as following. So first of all, I would like to give some motivation to new engineers that are present in this talk. I want to very briefly tell why I think that this is a great time to step into magnetics, to step into power electronics, and why, as I think we are like now in this moment of the next breakthrough. And I believe that power electronic engineers, magnetic designers will be very trendy and very needed in the future. Then I would like to very briefly cover four reasons why you should consider FEM simulation software. Then I will introduce our solution, TRAFOLO. I will very briefly show you what are those next steps you could do to start using it. And finally, I will demonstrate you the software itself so that you can get very brief overview what are the functionality, what is the workflow. So those who are familiar with some other commercial tools or free tools for finite element modeling, you might get some I don't know, like conclusions out of that. You could see what is the main difference between our solution and those other solutions. And I will use this chance to introduce and show you what new features we are currently implemented, and those new features will come in the next few days, probably today or tomorrow. They will be available for users. So let's begin with the trend. Why magnetics and power electronics are important. This is how we see the picture. So about 100 years ago, the main technology to create magnetic components, transformers, inductors, was to use electrical steel. And this is up to today. We are using a lot of the same similar design to construct large transformers and inductors because they are cheaper, but also they are highly efficient for low frequency applications. The next breakthrough has happened at about 50 years after the first, let's say, design of those transformers, with introduction of new materials. To be more specifically, like composite materials or ceramics that we nowadays call ferrites. With new materials that have significantly lower electrical conductivity, we were able to use higher frequencies. As a result, scale down the size of our transformers for the same power output. The next breakthrough has happened at about 30 years ago with introduction of more, let's say, even smaller components, planar inductors and transformers. And as I see that the reason why it took quite a long time to transfer from just plain, let's say, ferrite core magnetics to planars was because planars they require a higher degree of engineering because they're, as you know, that there are capacities involved and it's more challenging to let's say to etch them and manufacture, so that takes some automatization. So people got resolved those complexities. They introduced planar magnetics, and we are nowadays using them a lot. And as I see, the next big breakthrough will happen in the next few years, I hope, and it will be related to integrated magnetics. So magnetics that will be produced somehow similar to MEMS. If you are familiar with MEMS, then basically you can use technologies equivalent to like silicon chip production, but of course not such a small like nowadays, but basically on this larger nanoscale production machines, you can produce inductors and transformers. And this is very nice because then we could put it closer to the actual chips that will use those magnetics, and hopefully they will be more efficient and cheaper on that. So as we see in the future, we will have a lot of those smaller components embedded in all kind of electronics. But the reason why I'm talking about this integrated magnetics is because they're even harder to design using analytical or empirical methods. They will involve more and more some kind of simulation software, because as you can see in this case, so this path for conductor is quite complex. So representing it with some simplified equations would be a big challenge. Let's talk about the main reasons why FEM is 3D FEM is a great tool, let's say, in your toolbox. It should not be the only tool, but it should be like one of those tools that you will use to design components. And the first reason, as I see, is that very often assumption that magnetic flux is uniformly homogeneously distributed within the core is not holding true. So although ferrite core manufacturers, they try to balance this magnetic flux between the central limb and side limbs, this is not always the case. And if you will use some simple equations to basically calculate magnetic fluxes, inductances, and losses, you may get error. And this error will depend from case to case, obviously. Another thing that FEM allows you is to treat core saturation. So once you exceed some saturation point, the need point in your BH curve, the things start to get more complex for classical methods to calculate magnetic flux values. So with FEM, it can very accurately find out those regions where the core gets saturated and resolve such problem. But this is not all. So there, with the magnetic field non-uniformity, you also get losses unevenly distributed. So for most analytical equations that you would use, like Steinmetz, you would just feed your average magnetic fluxes and into those equations and calculate those losses. But this is not always true. For example, in this case that I'm showing here, you can see that the loss density for the central part of the core and on those outside limbs, so the difference is about 2 times. So if you would calculate the average losses in the core per volume then obviously that could be somehow in between maximum and minimum. But this is very challenging to estimate if you don't have 3D tool on your hand. And also note that those core losses, they are typically not linearly dependent on the magnetic flux density. They are typically like more closer to the being as a square. So every 20% in this magnetic flux estimation would add 40% error in core loss, about that. So the second reason why you would consider to use 3D FEM is to treat complex 3D geometries. To be more specifically, with oftentimes with some planar windings, we get non-symmetrical turns that exhibit that have all kind of strange effects. For example, proximity effect. So in this case, you see like those horizontal edges, faces. They are basically this is symmetrical case. So those faces are faced to the opposite side of this turn, where currents are flowing in the opposite direction. So you end up with proximity, basically effect, trying to those currents to attract. So therefore, we see more concentration of currents in those edges where our inductors bend. We also see more losses. And again, that could be very challenging to calculate any other method than 3D FEM. The next reason why 3D FEM could be useful is to treat losses in all other parts of your component that are not core and coil. Typically, such parts are brackets or clamps that hold together your core. There could be like simple clamps for ferrites, or like in this picture here, so those could be aluminum, like aluminum plates that hold together the gapped core. Heat sinks also, if you don't like design them well, then you could get some eddy currents there. Shields, all kind of shields that could be more related to wireless power transfer. But still, for magnetic components, you also have some metallic parts around to shield it from other components. All kind of external conductors. Those could be wires from whatever that comes close to your component, and housing. So although the most flux tries to follow the magnetic path of the core, there is some fringe flux and there is still some flux escaping your component and introducing some losses. So with 3D FEM you can account for them. And what is interesting with this particular case, if you apply such brackets or clamps on a gapped inductor and place those metallic pieces between the coil and core, if frequency is high enough, and then you get very high losses near those gaps due to fringe flux. And those losses could be comparable to the winding losses in your overall component. So if you make some mistakes in your component, then they could be very costly. So FEM could help you sometimes to eliminate them. And finally, the fourth reason why you would consider 3D FEM software is coupling with thermal simulations. So let's say there are not so many options how you can accurately calculate heat transfer. The most accurate could be like solving so-called conjugate heat transfer problem when you have heat conduction in solids and fluids. So fluids, air that takes some heat out of your component. Then if we reduce the and those simulations are very complex and very complex to set up. If you if we try to simplify, then the next type of thermal simulations that could be used with FEM is by basically solving heat transfer within the solids and approximating on boundaries, approximating with some boundary conditions the heat removal from your component. And this is how TRAFOLO treats heat transfer problems. So you can basically feed losses that were computed from harmonic or transient electromagnetic simulation. You can feed those losses into steady state or transient heat transfer solver. Steady state would be probably the preferred option to basically calculate quickly the temperatures that will be under specified load for a very long duration. Transient simulations, on the other hand, are very handy in cases when you have, for example, very large inductor or transformer that takes very long time for heat to saturate. And then how do you measure typically the temperature in laboratory? You put thermocouples and you basically record those measurements, temperature measurements in some longer period of time to see how the temperature rises. And then you can compare those measurements with FEM simulation, transient heat transfer simulation. And if results are matching, then it means that you have a very accurate model that represents heat capacity and heat conductivity of the entire system. Speaking about TRAFOLO, so TRAFOLO is a specialized software tool that we have started to develop about 2 years ago. I and my co-founder partner, Mark Skoncevich, we're located in Latvia, by the way, in Europe. And yes, so we try to build a tool that engineers would like to use, especially those engineers that do not have much FEM modeling experience, that are not professional FEM modeling experts, because from more experience, in order to be a professional in computer simulations, you basically have to do it as a daily job. So your company has to purchase a very expensive commercial license, and then you have to use that software like nonstop all days. But what is the reality in most companies is that there is no one person, a dedicated person, who can use the software like as a full time. So typically those are project based, and the person who is using the software just forgets what was that feature that I used last time to do that and that. So ideally, if you have like simplified workflow and support, that responsive support that can help, and this is our main, let's say, advantage that we try to provide. Speaking about the workflow, so we could break it into three main parts. So the first one is setup, that involves setup of just telling the software what are electromagnetic and heat transfer simulation you want to solve, provide all geometries. Then in the next stage, the software helps you to mesh your computational domain, and if needed, you can adjust that mesh, and basically create simulation files and start solving. And finally, you get results. And TRAFOLO provides you some pictures and tables with all the information that you may need from the software. But additionally, you can manipulate with those results to basically see more deeper where are those losses located, where are those hotspots, and so on and so on. So we try to basically include many different templates in the software, and we are updating existing templates by increasing, let's say, the precision and accuracy of those templates, but also we are adding new templates for new applications. So it's very likely that if you have a challenging design for your magnetic component, then if you reach us or Indian partners, then we could match your problem with some template and solve it in a shorter period of time. So if you want to try the software yourself, you can go to the webpage trafolo.eu. Under the download page, you will fill in the form and obtain the software. So you will be granted a trial license. And considering that most of you are from India, so and we are in Europe, it is more convenient for everyone to for those who are in India to contact our distributor, Reliamotive Labs. So they not only distribute the software, but also provide support and communicate. So if you have any questions related to the software, do not hesitate and ask them. They're very responsive and nice and friendly. That's it for the presentation part. And now let's get our hands, let's say, dirty. So let's see how the software looks. If you have any questions, and I think you might have, no, there are no questions. If you have any questions, please type them into chat. I will have chat window open it, and I will try to reply. Yeah, so anytime. And now let's start with the demonstration part. So the first time you install the software, you will get the window with all those templates that I showed you present. So once you create a project, yeah, this is a list of templates that are available within the software. So starting from inductors made of electrical steel, computation of inductances. This template shows how to import complex CAD geometries. This one is very interesting, a soft magnetic core made of basically a composite material. Dual active bridge topology. So this is transient simulation for transformer. Induction heating is just a very fun example to demonstrate the similarities between magnetics and inductive heating applications. High frequency inductors demonstrate how to use advanced meshing techniques to resolve skin layers. So we are using so-called boundary layers to resolve those skin layers. Toroid inductor flyback transformer is another notable example for transient simulation. So with all those transient waveforms, yeah. So we have now the first question. I will read it so that I can reply to it. Do you have different core model templates in the software? For example, ferrites, ERM, ATQ, etc., or is it possible to export for any 3D modeling software? So first of all, you can import any CAD geometry. And second, let me load this template. I will demonstrate how you can create geometry for your core yourself. So in this case, this core geometry was imported from a CAD file. Yeah. So I typically advise eliminate those unnecessary holes and all complexities. So basically try to clean your geometry. But this was just a nice looking core, so I decided to use it for this template. But here in source, you can choose that you want to create your core from template. And now in Geometry Builder, you can select all kind of core templates that are available. So starting from 2-limb, 3-limb, 4-limb, 5-limb, 6, 7, 10. I'm joking. So toroids, box geometries. So there are many templates that are unified. In one template, you can basically design many different shapes that could come with different names, typically as a specification. PQs and so on and so on. So what you do to create a template, you just select this type and specify some dimensions. Click apply, and the core will be built. And this applies for all templates. So next time, if you want to let's say to change your core to a different type, you would just adjust those parameters or choose a different type. Additionally, for those templates, you can add gaps. So there are two types of gaps. I will not go into details at this time about different gap types and so on. Just very briefly try to show you how you can create a gaps. for such a tree limb geometry. Let me increase this size. So let's say that we want to make a gap on the central limb of this geometry. So you see that now there are no gaps, and now I click on this new gap. I specify that I want to create a gap on the central limb, and I tell what are those coordinates for the max and min coordinates in this vertical z direction. So for example, here it will be, let's say, -1, and here will be 1. And once you click apply, so this is our gap. So next time the software creates assembly for the core, it will treat this part of the core as a gap. So in such way you can make as many gaps as needed. Yeah, I hope I answered your question. So let's very briefly go through other templates that are available. So there's some ideas about wireless charging, how you can use the software. Wireless charging is a new application that we are now also starting to focus on to include features that are handy not only for magnetics but also for wireless power transfer. So once you learn about wireless power transfer, you will find that there are many similarities. It's just a few features that are more in one or another application that are differentiating them. Pure heat transfer simulation. So in this software, you can also solve only heat transfer problems. I see that there are other questions. How about different material such as ferrite, nanocrystalline, amorphous, etc.? Also for the gap, is it there a possibility to use materials of different permeability in the gap? Let's start with the last question, whether there is possibility to use materials of different permeability in the gap. The answer is, I think, yes. I have never tried. So typically we set gap as a FR4, for example. So it has no permeability, but if you decide to make a core made of different, let's say, pieces, then I think yes, you can do it. You can do it. But I will need to try it myself, as this is an interesting case. And the question also was about different material types: ferrite, nanocrystalline, amorphous, etc. So from simulation software point of view, the difference between materials is basically in core materials is basically in two models. One model is related to core loss, and another one is related to BH curve. So basically, once you describe your material with BH curve and core loss, then you can define most of those materials that you mentioned here. What we cannot now treat is anisotropy in material permeability. So for example, this is very often in cold rolled electrical steel. So you have permeabilities different depending on the rolling direction. So with this software, we cannot do that, but we can add that manually to the model. So once you create the model, you can add manually different permeabilities anisotropic. And speaking about some other methods, there's actually another method that is being used in the software. It's called laminate stack model that allows you to treat this effects of eddy currents being, like, let's say, introduced in electrical steels, and this, let's say, phase shift, I guess it happens. Well, I'm not very detailed into this topic, but basically what you can do is to account for laminations in your electrical steel cores. Yeah, and let's use this chance, since we opened a material library, what you have to provide for the core. I will now choose the core that has more materials, more data. So first thing is that what you need to provide to the software is either BH curve or relative permeability. Obviously, if you have just a relative permeability, this is a simple linear problem. If you have BH curves, then it's a more complex problem. The software helps you to extrapolate this into saturation region, so that this differential relative permeability drops to 1. And what else? Core loss. So you can load core loss data as a CSV or Excel file, and the software will find fit for Steinmetz coefficients. So basically, you can tell the software whether your losses are in watts per kilogram or watts per cubic meter, and then you load import the data, and it will calculate Steinmetz coefficients for you. Yep. Let's continue with templates. If you have any questions, then sure, write to the chat. Further, yes, wireless charging. This is type of wireless charging with some implant. So this is like a medical application, equivalent to medical application. Heat transfer. This was very interesting articles that we found. Use of hybrid and foil lids to reduce the losses in a foil winding. So they put on top of those foil windings, they put 1 turn of lids wire. There's special numerical techniques to treat high frequency applications, so that you don't need to resolve eddy currents, skin effect, like volumetrically, but it basically treats currents as a surface currents. Planar winding mixed with lids wire. This is a simple planar inductor. Bus bars. So if you have like 3-phase bus bars connected to a large transformer, you can do electromagnetic and thermal simulations here as well. Planar transformer. Well, choke, as it says. This is also a new applications that we are now targeting is linear solenoid actuator, and finally resonant wireless power transfer. Let's open the case. Typically I use this one for demonstrations, and let's start from the scratch. I will very briefly go through the workflow so that you get the main idea, and those who are familiar with FEM, commercial FEM tools, so you will see the difference. Because the idea here is that TRAFOLO will try to ask you only those parameters and settings that are needed at that particular moment to set up the model. So if you have used other tools, then you have to basically jump from one place to another place, choose different parameters, and so on and so on. Here you specify symmetric full geometry, choose electromagnetics type, heat transfer, select and load materials that you want to use. So we are using different databases, and we are getting those materials. One of those databases is Open Magnetics. So, for example, Ferrex Cube materials, they are sourced from Open Magnetics, and for Ferrex Cube we have information about, well, it has only relative permeability, but it has full core loss data. So you copy those materials that you want to use, you import or create from templates your geometries for core, coil. Coils can consist of multiple coil groups. So now in this step you define only geometry. Later, the software will ask you to tell which is primary and which is secondary winding. So in this step you're only dealing about geometries. You tell how many turns are within this solid object. There 24. Fill factor was calculated, and a proximity factor. So if there's some heat sink, you can create it from template as well. Bobbin in this case is used only for capacitance, calculating interwinding capacitance, and heat transfer. So as I told before, we are not solving complete conjugate heat transfer problem with all those fluid dynamics and solid and heat transfer in solids. No, we are simplifying the problem. So, and in order to have a heat transfer between coil and core, we have to put some medium between them so that this heat will get through this bobbin. So we are adding the bobbin. This is sampled geometry. This is symmetrical case. Therefore, you see that the geometry was sliced in half. There's an air domain that was created automatically for components with core. You don't need large air domain. For air gapped, for air core inductors, you need very large air domains. But software will do it for yourself, for you. Make sure that all types and materials were identified properly. In this section, you have to tell how many windings you have. In this case, this transformer, so we have only primary and secondary. We tell what is the excitation. So primary and secondary will be excited with current. In this place, we can choose which is primary and secondary and how individual turns are connected within this geometry. And they are connected in series. So those individual turns are connected in series. Further, it is not needed in this case, but if needed, in some cases, you can change terminals. Just by clicking on them, you can change their position. You can tell which is positive and negative. Next, so the software automatically draws the circuit for you. The software knows that the excitation of coils is through currents. Therefore, it adds those two current sources. So basically, current goes through your FEM windings and to the ground. If needed, you can add additional inductor, resistor, capacitor. Those are called linear elements, linear circuit elements. Yeah, non-linear would be, for example, diode. And linear, they have time derivatives, constant time derivatives, as I understand. So you can add more components here and tell what are those connections. So those are basically node. I forgot the name. So basically, those are nodes for those elements. So you can tell the software how to connect. You click apply, it will draw a circuit for you. Next, you import the waveform. In this case, this is flyback transformer. Therefore, the waveform is quite challenging. So we imported this waveform as a CSV file and tell the software what is the frequency, how many periods we want to solve, and how many points we want to basically solve in FEM software. You may ask why we need to tell the software how many points we want to solve. If you look on the waveform that was imported from Circuit Simulator, you may see that here a lot of points at current equal to 0. So for FEM simulation, it's just a waste to simulate that. But then you have sudden change in the current, so it goes up to the maximum. And there's just only one point here, and then it suddenly drops down. And for FEM, this is like a nightmare. So it will have very hard time to resolve this time derivatives for this sudden change, and might have issues with convergence. So what do you need to do? You basically have to interpolate this waveform on better waveform. And TRAFOLO helps you to do that. So this is improved, optimized waveform. So we have only 2 periods here, and it tries to add those additional points so that the sudden change is not as sudden. Additionally, if you need, you can look on DFT, discretization for primary and secondary waveforms, to make sure that everything is good. In some cases, actually, I found that circuit simulators, they put some DC bias where it should not be. In this waveform, well, if you do a DFT, you will get a DC bias. But in some other transformer topologies, for example, dielectric bridge, you should not have DC bias. And if you see the DC bias in these DFTs, then you are basically in trouble because you will not calculate what is actually the actual losses, for example. But anyway, further, you can specify the number of harmonics you want to use to calculate losses in windings. So the losses in windings in this case is calculated as following. So for each of those harmonics here, for each of those frequencies, using Dowell equation, the software calculates R AC, R DC coefficients for each of individual windings, and then calculates average, not average, but equivalent R AC, R DC coefficient for the particular coil winding for the entire frequency range that is used. So it's a bit tricky. If you have more questions, we can discuss this after this webinar. But the idea is that yes, you have to tell what is the accuracy of your resolution, loss resolution for windings. Additionally, if you click on this button Harmonize, what software will do, it will break your simulation into harmonic simulation. So it means that instead of transient simulation, it will solve it into harmonic notation using complex numbers. And for flyback transformer, you should not do that. But for some other topologies with signals or excitations close to sinusoidal, if you, for example, have one sinusoidal, like the base, let's say, frequencies, like with high amplitude, you have a pure sinusoidal, and then you have some additional noise. Then you would better go with a harmonic simulation, where those frequencies will be solved independently on each other, and then those losses would be summed together. Anyway, speaking about heat transfer, so here you have to provide the boundary conditions. So to tell the software how your heat is removed from your computational domain, from your component. And there are many options. So first option, you can use convection for those boundaries that have some airflow. And then you have option of two parameters. Basically, with those two parameters, you approximate very complex heat removal, but very simple model. If you find those coefficients well, then you might get quite a good agreement with experiments. But finding those two coefficients, external air temperature and heat transfer coefficient, takes some, let's say, trial and error. Further, if you have some fluid cooling, liquid cooling, then you could use fixed temperature. For example, if you have a component with some pipes going through between, let's say, winding and core, and cools down, then you can, on those internal heatsink boundary conditions, you can set fixed temperature equal to the temperature of fluid, because fluid has very good heat conductivity and convective heat removal. So you can play with those parameters and basically solve quite challenging, very broad spectrum of all kind of thermal problems just with those simple coefficients. And you can set those heat removal types not only on the entire component, but you can be more specific. For example, you can select the specific phase and apply those conditions only on it. There is a question in chat, so I will read. Does it consider increase in AC resistance due to resistivity changes and hence final winding losses? Due to resistivity changes? Yes. So if you mean change in resistivity due to eddy or proximity effect, the answer is yes. For solid wires, it solves and resolves those currents accurately. Well, it basically resolves the actual current, how it flows in those solid wires. If you are talking about, for example, Litz wire, then things are a bit more complicated, because for Litz wire or stranded wires, before the simulation, you have to tell the software what is the frequency, what is the conductivity of material, what is the strand diameter, and so on and so on, so that so the software can use double equation to basically calculate RAC, RDC. Yes, so speaking about temperature change, so you can do weak coupling between electromagnetic and thermal simulation. So weak coupling means that electromagnetics and thermals are solved separately. First you solve electromagnetics, then those losses are passed to the heat transfer solver. Then the temperature distribution can be given back to electromagnetic solver to adjust the conductivity of materials and recalculate the problem again and pass those losses to heat transfer solver again. So you can do those weak coupled iterations, and it is possible to do it using these temperature iterations. So if you select any number larger than 1, since the software will do those additional loops for you, it will take longer for simulation. Obviously, if you select 2, then your overall simulation will take 2 times longer. And if you choose 3, then you get 3 times. But yes, you can account for those temperature dependencies. And RDC change. As I understand, you mean probably, I hope, RDC change due to temperature. So yes, the software can account for that. So temperature dependencies can be accounted. As initial condition for the temperature, you would specify this steady state temperature predicted. You tell what is the initial temperature. So it will basically, what the software will do, it will take this temperature, and by knowing how copper conductivity, electrical conductivity changes with temperature, it will adjust this conductivity. So this is temperature coefficient that is basically accounts for those additional resistance due to higher temperatures. So yes, this temperature here is initial one, which you predict. Tell the software that this is going to be my initial guess. Then if you choose more iterations, then it will automatically start updating the temperature and feed it to electromagnetic solver. Okay, so if you would have electromagnetics disabled, then there would be additional option for heat sources. So you could tell the software that I have, for example, 10 watts in windings, I have 5 watts in core, and then you would have pure thermal simulation. So you can do those simulations very easily as well. This is meshing step. So the software, by clicking on this button here, the software creates a computational mesh. Further, if you need some more adjustment and refinement, you can basically play with those parameters here. You just click on some group of bodies and specify either maximum edge size for that mesh, or you can choose some other algorithms, or if needed, you can specifically choose some faces to resolve. So there are plenty of options you can play with to basically get the right computational mesh. And those who have used FEM simulation software, you should know how important it is to have efficient mesh, because especially for 3D, because 3D are computationally expensive simulations, and you would aim for smaller number of elements. Those elements should have a good aspect ratio, and the refinement should be put in those places that have the highest gradients. Yeah, so you don't want to refine everything like with fine mesh. No. You just refine those places that have the highest gradients. For example, highest magnetic flux gradient, highest current gradient, or whatever you want to resolve. So just put the exact number in those specific places. Finally, You tell the software how many CPU cores you want to use. So TRAFOLO has no limits on CPU cores. If you have a computer like with 64 cores or with 1000 cores, so go ahead, you can use it. And yeah, so the way how you would treat nonlinear system, so all you have to do is click on simulation setup and run simulation. Once the simulation is over, let me open already solved case, because at this moment we can look here. So this will be results that you will see immediately after the simulation is complete. This particular simulation took almost 3 minutes on my computer to run, and you will get loss data, integrals, the total losses, RDC resistances. There will be no RAC resistance because this particular is transient simulation with very complex waveform. So there's no one specific RAC resistance. What else you get? Hotspot capacitances. Yep. Then you have proximity coefficients, proximity losses, or those RAC, RDC coefficients that were used in the software. So they will be present here. Further, you have magnetic flux distribution in time, so you can play it as a video if you want. Slow video. Well, video don't want to play today. Yes, so coil losses, obviously core losses, and temperature. And last but not least, if that is not sufficient for you, if those pictures are not sufficient for you, then you can open results in ParaView. ParaView is a post-processing tool that we natively use for visualizations. You click on this button and then results will be loaded into ParaView, and then you could have a more detailed analysis of your results. You could not only, of course, rotate, but also like do some integrals, calculations, plot vector fields to show how currents are flowing in your design, how magnetic flux lines, and so on and so on. So so it takes some time for transient simulation to load. If you have any questions, please go ahead. We don't have much time. I expect to finish like in a few minutes. There's one question. Is there a frequency limit? Is there a limitation in number of nodes in trial version? Last question, what is the main limitation of TRAFOLO in simulating magnetics used in power electronics? Mainly AC, probably you mean AC, DC, and DC, DC. So let's start with the first question. I will answer questions now, and then we will follow with post-processing, okay? So first, about frequency limit. Technically, there is no frequency limit for this solvers that we use. What matters is the difference, the ratio between the size, characteristic size of your component and skin depth. So skin depth versus magnetic characteristic size, what matters? So for example, solving a low frequency large transformer would be equivalent to solving small high frequency transformer, because this skin depth and characteristic size ratio would be identical. Further, of course, there is some limits if you go into those very high frequencies. Then I think that the solver is not accounting for capacitive effects and for electrical field, electrical field and magnetic field coupling. So the solver is as typically it would be called low frequency solver. So it is able to solve, let's say, 2 megahertz easily, or maybe even 100 megahertz easily, but I would not use it for gigahertz and for radios until megahertz. I would say that megahertz okay, but gigahertz I'm not sure. I'm not competent to answer that. I think capacitance effects are not considered here, therefore you will be in trouble of solving it. Yeah, and there was a question about number of nodes in trial version. So there is no limits in trial version except time duration. So you get the software. You can ask us and our partners in India for help to get used. We can help you to set up your problem so that you can make sure that the software works as it is desired for you. We will try our best to help you solve your case, but we of course do not guarantee that we will be able to solve your case in this limited time period, but we will try. And how about treating AC DC DC DC? Yes, easily. So with transient solver, as I showed you here, you can treat any waveform. As I consider, DC is basically identical to AC, but with a zero frequency. So yeah, this is how we often treat DC biased simulations. Is trial also available for industries in Europe? Yes, so you can, from everywhere in the world, you can get a trial. So you have to go to our webpage, fill in the form, and you will get the license key to your email immediately, within a few seconds. And you can start using it. Note that it might take many gigabytes of memory on your computer to download all packages, because we are using open source software a lot. For example, Salome platform for making CAD geometries and so on. And that is very large software. I will just open it to demonstrate it, but let's do it later. Very briefly about post-processing. So this is another tool that you will easily install on your computer. This is open source free post-processing tool, Parview. So what TRAFOLO will provide to you is, so it will basically load results, simulation results, and you will see those previews for your results. So you will be able to choose the time, then select the fields that you want to show, and so on and so on. So it might take some time to play for you to get used, but once you learn how to use it, it will be nice tool in your let's say toolbox, because this is very universal and very powerful post-processing tools that you can use not only with TRAFOLO but with some commercial tools, other tools as well. So very handy. There are many filters available, so you can apply them on that result data. I will not go into details, just show you that there are many of them. And yes, I told about the Salome platform, just mention it. So you can use it as a CAD editor. Instead of, let's say, SolidWorks, you can create some primitive geometries here, and then fuse geometries, do Boolean operations, and so on and so on. And then you can, of course, load those geometries in TRAFOLO. We advise you to use TRAFOLO templates whenever possible. Yeah, but if you need to manipulate with your geometry, then well, you can use this CAD editor. You don't need to purchase, for example, SolidWorks. What else? You can manipulate with geometries that were produced by TRAFOLO. For example, here on the top, you click on the folder name of this case under CAD. You can, for example, there's core.eges. I copy the location of this file, then I go to File, Import eges, just copy the file location, click Open, and as you can see, my geometry was imported. So now I can manipulate with this geometry in this editor. And yes, and then again export and import into TRAFOLO.